Clear? So first cycle we will discuss about Otto cycle. What will discuss? Otto first cycle, okay? Some people call Otto cycle, some people call Otto cycle, all are same only, never mind, okay? It's a name of a scientist, name of the scientist, Otto cycle. For which engine we will use Otto cycle? For which engine we will use Otto cycle? We don't call petrol engine, diesel engine like that. We call only two types of engines. What are those? No, not four strokes, two stroke, not like that. Yes, what we call? It's a common name, right? All engines are called internal combustion engines. When combustion takes place inside, we call it as internal combustion engines. So that is ruled out. Yes, what we call? SI engine. Do you remember what is the SI? Spark ignition engine. Second one, compression ignition engine. Right. So Otto cycle is used for spark ignition engine. SI engines we use. All light volatile fluid. All light volatile fuel. If you take ignition, it will fire. It will catch fire. It is not like the Sami movie where he will ignite and put into a diesel tank. It will exhaust. Very simply. Clear? It's not like that. Got it? So just will take, he will ignite. That's what called what? Spark ignition engines. Spark ignition. Compression ignition is not like that. When fire takes place, you have to pour the fuel. You have to pour the fuel to make more combustion. To make the more combustion. Got it? Got it? So where any gas you take, any gas, it works under SI engine only. It works under SI engine. Any gas you can take, not an issue. Got it? Any doubts? Okay? So tell me, in 4-stroke engine, how much stroke will be there? In 4-stroke engine, how many strokes will be there? What nonsense it is? In 4-stroke engine, how many strokes will be there? In 4-stroke engine, how many strokes will be there? In 4-stroke engine, how many strokes will be there? Sattama. 4-stroke. I give an answer. In 4-stroke engine, how many strokes will be there? How many strokes? 4 strokes. Right. Got it. I give an answer. I want to check. Okay. I want to check. You know, I want to check. Clear. In 4-stroke engine, how many power stroke will be there? 1 power stroke. He got confused. Many people got confused. Some are asking power stroke, not number of strokes. Some people say in 2-stroke 1 power stroke, in 4-stroke 1 power stroke. Clear? In 4-stroke engine, 1 power stroke only. In 2-stroke engine, 1 power stroke only. Clear? So 4-stroke engine will have 4 strokes only. How many process will be there? Satyama. So today you are going to explain me. I am going to draw the PV diagram. I am going to draw the, because last class I explained how the petrol engine, diesel engine works with respect to PV diagram. Also I explained to you guys, right? So today first we have to draw the PV diagram. That's very, very important, right? So I will write the PV diagram here. This is my PV, and also I will continue with my TS diagram also. TS diagram, right? Both we will do, okay? Parallel we will do both. And assume we have our engine here, right? We have our engine here, right? In last class we have seen that. We have our engine here, right? In last class we have seen that, right? We have our engine. Got it? So what is the volume? What is this volume? Assume this TDC. This one. Stroke volume. This one? Clearance volume. Very good, guys. Got it? So Vs plus Vc. Vs plus Vc. Total volume. Remember always, okay? Remember always, okay? So what is the first stroke in our IC engines? Sattama. Section stroke. During section stroke, what happens? Inlet valve opens. Exhaust valve close. Piston moves from TDC to DDC. During the stroke, air and fuel mixture will enter into the cylinder. But due to vacuum creation, you are right only. Due to vacuum creation, air will enter inside cylinder. So how it happens? My piston will start here. My piston will start from here. Here, a piston will start from here. There is a vacuum creation inside. Due to vacuum, some amount of air fuel mixture will be drawn into the cylinder, like our syringe. I explained in last class. Like our syringe. Again, vacuum, after filling, again vacuum creation, again continue to take place till the piston reaches to where? Where? BDC. This process continues till the piston reaches to BDC. Clear? But how it will be means it will draw pressure constant, 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 it will draw pressure constant. Each stage the pressure remains constant. And again vacuum, pressure constant, again vacuum, pressure constant. Each time it will take place. So what we do for steady case, we remove vacuum pressure. This one will remove. We consider the suction stroke. Doing suction stroke, it is a constant pressure suction. What will take? Constant pressure suction will take. Finally, we'll remove that. I'll tell you how it gets removed, okay? Understood? Stroke 1, how it takes place. Understood? So, constant pressure suction. What about the stroke 2? Stroke 2? Compression stroke. So, during the compression, both the valves close. The piston moves from BDC to TDC. It moves like this. BDC to TDC. So everything closes inside, right? Everything closes inside. What will happen? When I compress, what will happen? Pressure increases. Volume? Because I have pressure volume only. I have pressure volume only. Got it? I have pressure volume only. So what happens? Pressure increases, volume decreases. Got it? Clear? So it follows adiabatic equation like this. Volume reduces, pressure increases. Volume reduces, pressure increases. So we will stop here, okay? We will stop exactly. We have to stop here. We will stop here. So this is my state 1. This is my state 2. For the process, I have not given any name for this because I'll tell you at the last why we have not given any name for that. Got it? So when piston reaches to TDC, we will have high compressed air fuel mixture. Got it? High compressed air fuel like Otto bomb, Now what we have to do? We have to ignite. We have to ignite so that combustion takes place. Power will produce. That power will be absorbed by the piston. Got it? So at this place, I will ignite. I will ignite. During that time, we assume. Who will assume? We assume there is no change in movement of the piston. That's why it is when you ignite, it is called heat addition. What it calls? Heat addition. Got it? We are igniting, right? We are adding heat. Temperature will rise. Temperature will rise. We are adding heat. Got it? So this heat addition is considered there is no movement of the piston during heat addition. There is no movement of the piston during the heat. That's why we consider when I add heat, the pressure will rise drastically, right? Due to closed surface, right? So constant volume heat addition. This is constant volume heat addition. Constant volume, no stroke here because piston has not moved. It's not either moved forward or backward. It is on that place only. We assume constant volume heat addition. Remember always people ask what type of heat addition in SA engines. You will ask what type of heat addition in SA engine. Constant volume heat addition in SA engines. Constant volume heat addition in SA engine. Got it? Got it? Now we will come to stroke 3. What is stroke 3? What is stroke 3? Power stroke. After we are igniting, no, the heavy blast will take place. Heavy blast will take place. That blast will push a piston from TDC to BDC. So that power will produce. So that power will produce. Got it? So that's also when that is a type of expansion only. That's type of expansion only. Volume increases, pressure decreases. Here will be high pressure. And piston moves backward, what will happen? The pressure keep on decreases. Pressure keep on decreases. That is called as the that curve will be like this. That curve will be like this. So suction, compression, heat addition, expansion, power stroke. Got it? After this, the entire power drawn. The entire power drawn. The remaining heat will be there. A small amount of heat will be there. Are we using that heat? We are sending to the atmosphere. Have you seen a movie? It's called Tani Varuvan. Tani Varuvan. Got it? There will be a local rowdies will be there. Gundas. What they do? They go and do chain snatching. When the people have in training, you remember that scene, right? So they plug the chain, they'll run away from there. The hero will chase the gundas, and finally they will abscond, right? So what will hero do on that place? He will take water bottle. He will take because he want to know which bike came early, right? So he will pour the water. Where he will pour the water? On the exhaust, because the exhaust has high temperature. Even to rise 1 degree Celsius, what we have to do? We have to burn some fuel. Fuel where we get? Dabbu gaza, dabbu. We are purchasing fuel, right? We are purchasing fuel, right? Everything is dabbu, right? Everything is double, right? In class wow, uniform clear. So you want to check. Clear. So even if you want to rise 1 degree, we have to burn some fuel. Burn petrol. Have we get free of cost or what? No, right? We have to give money. Any fuel, we have to give money. Got it? So there you will check how much temperature has exhaust. Similarly, after attaining entire power, still we have some heat. Still we have some heat. That heat is sent to the atmosphere. Engineers are fighting to extract more heat. That's why we have turbocharger. We have seen, right, turbocharger. You have seen, right? So engineering keep on fighting to extract more heat. But still we lose some heat to the atmosphere. That heat loss will not give any work. Or it will consume any work. Amalia, in which process work done will be zero? In which process work done will be zero? In thermodynamics, at which process work done will be zero? Constant volume. If there is a change in boundary, work will produce. There is no change in boundary, no work will produce. So in which process work done will be zero? Constant volume. Because after extracting large amount of heat, even though we have small amount of heat, due to that we don't extract any work. That's why that heat is considered as constant volume heat rejection. Constant volume heat rejection. Clear? So stroke 3 only over, right? Still we have one more stroke. What is that? What is that stroke? Exhaust stroke. What will happen exhaust stroke? Exhaust valve opens. Inlet valve close. Piston moves from BDC to TDC. It will push all the gas. It will push all the gas. Clear? How to push the gas? It has to increase the pressure in the cylinder. It has to increase pressure. It will increase the pressure, some amount of gas will escape. Again, it will increase the pressure, some amount of gas will escape. So that means at this place, the process will be like this, opposite to the section. Opposite to the section. Pressure rise, it will send to atmosphere, remaining constant. Remaining the same way it will maintain. So for study case, what we do? For study case, what we do? Again, this process takes us a what? Constant pressure exhaust. Constant pressure exhaust. Got it? This is expansion. This is compression, right? Amalia, this is positive work or negative work from TDC to BDC? Positive work. From BDC to TDC, negative work. One positive or negative will happen. Get cancelled. That's why this process we never use. Suction exhaust or ideal stokes we never use because one gives positive work from decision to decisions. The other one gives negative work from decision to decisions. Both will get cancelled. Both will get cancelled. So we have only 2 stokes, not 4 stokes here now, right? Right? Suction stroke we neglected. Exhaust stroke we neglected. So what stroke remaining here? Here. Compression, power stroke. We have 2 stroke. How many process? 4 process. What is the process? What is the process? Has no suction. What is the process? First process. Compression, 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 ignition, expansion, rejection. Clear? Compression, heat addition. Compression, heat addition, expansion, heat rejection. We have 4 processes. How many strokes? 2 strokes. Let's see TH diagram, right? Let's see TH diagram, okay? In TH diagram, you can see the same process takes place. Clear? At state 1 we have here. At state 1 we have here. Here you can see we have one similar same place. I told you this process is a adiabatic compression, reversible adiabatic compression. In adiabatic, Q is equal to constant. What about in reversible adiabatic? In adiabatic, Q is equal to constant. Huh? Q is equal to constant only. One more term also will be constant. What is that? In reversible adiabatic. Satyama, entropy constant. If Q is equal to constant, it's called only adiabatic. Even entropy, there is no change in entropy. That is called reversible adiabatic. That is called reversible adiabatic. So the state 1 to 2 will be straight line. State 1 to 2 will be straight line. Here, during heat addition, what happens to temperature? During heat addition, what is the temperature? Will increase or decrease? Will increase or decrease? Increase. Entropy? Both temperature and temperature and entropy are friends. If temperature increases, entropy also increases. So the same curve will be there. Again, this expansion is a reversible adiabatic expansion. Again, entropy will be constant. Got it? During heat rejection, temperature decreases, entropy decreases. So this is QS, this is QR. Take S1 is equal to S2. Here you take S3 is equal to S4. Here you take V1 is equal to V4. Here you can take V3 is equal to V2. This is also constant volume heat rejection. That's it. Copy these 2 diagrams. And we will see one by one process, okay? We will derive one by one process.